So it's like I get double dose of partial fractions today. Okay, so if we had, if we had an integral like this,
You're supposed to write this down, or just like
you wouldn't have to. Okay, if we had something like this, it's like set up perfect for us, right? Okay. We could let u equal x squared plus 10x, and du would be 2x plus 10 dx, and that's perfect for our u substitution, right? Because our numerator is x plus 5 times dx, so we can just balance this out with a 1/2, right? And we would have 1/2 integral of 1 over u du. And that's perfect. 1/2 natural log. And we plug back in. Now, what if our numerator was x plus 6? Well, then we're screwed, right? Okay. However, if we could break this apart to where we had a constant over a linear denominator and a constant over a linear denominator, then we could easily use our natural log rule, right? Don't write this down. Could we take those antiderivatives fairly easily?
yeah. Yes.
3 natural log of the absolute value of x plus 1 plus 5 natural log of the absolute value of x minus 2, right? Boom, easy, okay? So what partial fraction decomposition allows us to do is it allows us to take a fraction and we can break it up as the sum of multiple fractions, okay? Do you want me to review the specific rules, or do we want to just like go into an example to remember what it's like?
Jump in.
You're ready to jump in? Okay. So let me remind you of a couple things. We'll just do it very informally, okay? Whatever we have, and we always want to see if u substitution is going to work, right? And we always want to be kind of in the mindset of if I have that special x squared minus a squared or a squared minus x squared or whatever, there could be a possibility for trig substitution. But if we have a rational where we have polynomial over polynomial, that's the important. We all have to be polynomial for numerator and denominator, then we can break it up. Okay? Whatever the denominator factors to, however many factors are, that's how many fractions we can break this up. So this one, if we were to perform partial fraction decomposition, we would break this up into 2 fractions, one with a denominator x and one with a denominator x plus 10. Okay? If our denominator is linear, we have a constant numerator. If our denominator is quadratic, we have a linear numerator. Okay? It's always just 1 degree less on top.
What if it's not like it can't be factored, like there's I in it or something?
So that's when we keep the factor quadratic. Like if you have x squared plus 4, we would consider that a quadratic factor to where we would write a linear numerator. Okay, and we'll do one of those to see. Okay, so let's jump in here. Nope, not squared. Not squared. 8x plus 82 all over x squared plus 3x minus 10 dx. So this is a technique that you learned 2 years ago. We need to refresh. But once we do the decomposition, the integration is the easiest it's been all chapter. Okay? Okay, so our first step is we need to factor our denominator. Okay. What is our denominator factor to?
X plus 5 and X minus 2.
X plus 5 and X minus 2, you said?
Yeah.
Okay. How many factors are in our denominator?
2.
Okay, not a trick question. Okay. That's how many fractions we're going to pull this apart for. One with a denominator x plus 5 and one with a denominator x minus 2. Okay. Since we have linear denominators, each of our numerators will be constants. Questions so far? Okay. We are then going to multiply. Whatever your denominator was that you factored to, that is exactly what you are going to multiply by. The whole purpose of this is so that we no longer have fractions. So we're going to take our least common denominator and we're going to multiply by it. So what happens when we take our least common denominator and we multiply it over here? We get 8x plus 82. What about here? When we take these two and we multiply it to this a fraction, what happens? I would like your input.
8 times X minus 2.
Okay, the x plus 5s cancel and a gets to be multiplied to x minus 2. Okay. Same thing here. If we multiply to this guy, the x minus 2's cancel and b gets to be multiplied. Okay. So there's two methods that we talked about in pre-calculus. Okay. We'll talk about when we have linear denominators like this method's going to be easiest. And on the AP test, a majority of your partial fractions will be linear like this. Okay. So we can. Okay. So now we need to solve. Okay. What would be a number we can plug in for x that would make a disappear?
2.
Let's do it. Let's plug x equals 2 in to where we get 96. Nope, 98, because 16 has to add to the 2. Just kind of drops the 2. 98 equals, when I plug 2 in here, poof, gone. And we have 7b. So b is 14. Now, I'm leaving a few of my steps out as far as plugging in, but can we plug in our head? Is that okay? Are we okay with that? Okay, I don't want to throw anyone over the edge. I know last week you got kind of mad at me. What should we plug in next? -5. And if we plug in -5, on the left side we would have 42. He says with enthusiasm. This would poof disappear, and we would have -7a. So a would be when I plug -5 in for x.
Okay.
All right, so now our integral. I don't want to go too far down here. So our integral started off as this right here, right? Well, now our integral becomes a over x plus 5 plus b over x minus 2 dx. All I did is we now take a and b and we Pop them back in. So now we have, right? When we integrate this, we get -6 natural log of the absolute value of x plus 5, and 14 times the natural log of the absolute value of x minus 2 plus c. Benjamin.
When we lose points if we forgot the absolute value sign of it?
Yes.
Okay.
Minimal, but yes, it is important. Now, if inside were x squared plus 5, the absolute value sign doesn't matter. But here it does. Okay. What?
Straight up and down line. The L's from the natural logs.
I know sometimes I'll do loopy L's just to get a little bit of a distinction there. Yes.
Would it be fine if we solved for A and B using a system of equations?
Yes. And I'll show you that method also. But not everybody wants to solve a system of equations, and so this is pretty cut and dry, right? Not a lot of thinking involved. Okay. We like to not think sometimes, right?
All the time.
All right. Example number 2. It is nice. Now, and I wanted to talk about this one because technically how many factors do we have? We have 2. So how many, and I guess let me take a step back. Do you notice how U substitution is not going to do us any good here? Because we have linear, and then our composition down here is linear, so that relationship's not there. And we don't really have anything for, like if this were maybe x squared plus 2, we could do a trig substitution, right? But x plus 2 is not helping us there.
But can't you just like have use x plus 2 and then just have substitute the x on the top for u minus 2 equals x? Is that not possible?
Like that?
Yeah, plus this. Yeah. Is that just like 2 rows?
You have 6u minus 19 over u squared.
I mean, I think that you could get there. I think either way you do it, it's going to be a little bit messy. Okay. So I think in this problem, you might be okay. All right, but let's look. Sometimes it's nice to have an option. Okay. So let's look at option number 2. Option number 2 would be to break this up in partial fraction decomposition. So we would take 6x plus 7 over x plus 2 squared. And you said that there are 2 factors, so we need 2 fractions, right? Well, what's one of our denominators?
X plus 2.
Okay, if both of them are x plus 2, can't I add them together?
Yep.
So when you have repeated factors, you have to give me all of the versions of that repeated factor. So if this were x plus 2 cubed, you would add one more with x plus 2 cubed. So you would have to the first, to the second, and to the third. So you need all of the powers when they are repeated.
Why?
Well, just like I showed you before, if it were this, I'd be able to add these 2 together because they have the same denominator. And we want that denominator. So we have to be able to get that denominator somehow.
So we just square one.
All of the powers have to be represented. To the first power, to the second power.
Okay. It feels like the 50th power.
Yeah. You would have 50 of them. I won't do that to you.
Like how
Now,
many letters in that?
this is linear. This is a repeated linear. So you still have constants for your numerator. Okay, yeah, you run out.
It'll be like double A.
Okay, so when we multiply by our LCD, we would get the 6x plus 7 equals A times x plus 2 plus B. Lonely B. Okay, what number can we plug in?
-2.
And if we plug in -2,
B would be
-5 equals, -5 equals B, because this would be -12, 5. 0 plus B. Okay. So, how do we get A?
You move B over and then plug in a number.
Okay, we only have B left, right? And so we know that we only have A left. We know that B is -5. Could we just choose a random number for X? Sure.
Sure.
What number would be easy to plug in?
-1. 0. I go with -1.
I kind of like 0.
Okay. But if you do -1, then it makes it so that that side is literally 1 and it's A times 1.
Okay, you do that, I'll do this. What's A?
It's 1. 6. I mean 6, sorry.
I saw the minus sign and I was like, oh, that's the dot because my glasses aren't here. So I thought you were multiplying it.
I don't know how it would be 1.
Well, it was like,
It's okay. It's okay.
Wait.
We're all okay.
where is my head today? I don't understand.
Do you have a question about this, or are you just upset at yourself?
I'm just upset at myself right now.
Okay. So we started out with the integral 6x plus 7 over x plus 2, the quantity squared dx. And that is going to become the integral of a over x plus 2 plus b over x plus 2, the quantity squared dx. Caleb, we are getting the same answer as you would with your new substitution. Okay, this is working out the same. Okay, so whichever one you see, you go for it.
Okay. So
Okay.
you wouldn't get counted off like on the quiz. You could
No,
use
but I'm
substitution.
probably not going to give you one that you'd be able to do any other way, if I'm being honest. Okay. All right. So what is this antiderivative? This one's nice, right?
6 and 2
Now this one, we need to think of as -5 x plus 2 to the negative second power. There's no natural logs when the power is something besides 1. Okay, so this becomes plus 5 over x plus 2 plus c. Because we increase the power by 1 and divide by it. That's the power rule.
Wait,
Yes.
I don't get why it's minus 5.
So we increase the
plus
power to -1.
Yeah.
And divide by -1. So it becomes positive.
But in the original arm, you subtract. Oh, that's where. Okay. That was,
Two negatives.
Are we good?
That worked out nicely, but also on my paper, both of my examples ended on the exact same spot.
Well, let's do a third example.
So that's good.
Okay, so this is what Caleb was asking about. Do we have to factor using I? No. We'll always keep it real. Okay? Pun intended. Yes, thank you. I think I gotta liven up the bunch today.
I'm proud. I'm
proud to have you as a teacher at that
I'm glad it only took until October 24th. But we can
It's 24th already, isn't it?
yeah, it's almost Halloween. It is a week away from Halloween.
Oh yeah.
It's going fast.
October.
Like November isn't a week from tomorrow.
I feel like October. I feel like October just went by like
Finalized
3 days.
What's wrong with November 1st?
Okay, so we really don't have a lot of options here. Okay? Yes, we probably could do trig substitution with x equaling radical 2 tangent theta, but some of you really don't like trig substitution, so if we have a different way, okay.
Yes.
And I don't know if this would turn out to be anything that would be nice. I don't know. But we do have the option since we have polynomial over polynomial, okay, and that doesn't always happen with trig substitution. Usually there's a radical involved, which is why we have to do it. But since we have polynomial over polynomial, we can break this up. Now we have 2 factors for our denominator, which means we would break this up into 2 fractions. Okay. Our first one is a linear denominator, so our numerator is a constant. Our second one is a quadratic denominator, so we would need a linear numerator. It's just 1 degree different for the top. Okay. Now we all understand that once we find these values, if we were to get common denominators and add them together, we get back to where we started. We're doing like the reverse of adding fractions together. Pulling them apart. Okay. You were saying hi to people.
Hi, Anthony. Hi, Anthony.
There you go.
You did it.
So are you okay with just don't want anybody to be
I didn't do it today. You didn't say anything
like
today.
that? Who did it today?
Hi, Nick.
I said hi, Nick. I
At
forgot
the
that.
very beginning?
Hi Nick and also Anthony.
Yes.
Just so
We
you know,
miss you.
Anthony, Matt forgot about you.
Hey.
We miss you. It's not the same without you guys here.
I bet they're not even gonna hear this.
They don't listen to it.
They don't listen to it.
But if they do, they'll feel warm and fuzzy.
Okay, do you agree with my multiplication? Okay, so what number are we gonna plug in to make that factor next to A go away?
Negative square root of 2.
Not really.
The square root of negative 2.
The square root of negative 2, which is not a real number, which we're not gonna worry about. Okay, so instead, we have a different option.
Wait, isn't it CX?
Yeah. Making sure you're paying attention. Okay. On the left, we have 1. On the right, we better have 1. So, ax squared plus bx squared. Is there an x squared over here? So a plus b better equal 0 because the coefficient of x squared on the left better match the coefficient of x squared on the right. And if there's no x squared over here, then ax squared plus bx squared better add together to be 0.
Oh, that makes sense.
Okay? Do you see an x term over on the left? No, so what should c equal? This is weird. All right, but our constant is 1, which means 2a better equal 1.
Who thinks to do this stuff? Like one day comes up with this method of doing things.
So A is 1/2. What's B?
One.
Negative 1/2, and we know that C equals 0. Okay? So our integral becomes A over X plus BX over BX plus C. C is 0. Now I know this isn't beautiful, and we can make it look nicer, but this is what our integral becomes. Should we just pull out the 1/2? Are you okay with that?
Yeah, that works.
Okay.
You need to make the x squared plus 2 equal to 0.
Okay. So this one we have a straightforward, like really straightforward, as straightforward as they get, right? We have 1/2 natural log of the absolute value of x. But over here, what are we going to have to use? We're going to have to use u substitution, where u equals x squared plus 2, and du equals 2x dx. So we're going to have to make this 1/4 the integral of 1 over u du. Because the 1/2's already there, and then we need a 1/2 to balance it out. So we have negative 1/4 the natural log of x squared plus 2. Here is where I would not take off points if you didn't get the absolute value signs, because it doesn't need it. There's your answer. Okay, we have 9.5, maybe 9 minutes left in class. I'm not here tomorrow, so let's at least do one of our homework problems before you leave, so that if you have a question, you can ask me while I'm here right now. Okay? So at least get one book open at the table and try the first problem to make sure you can get through it.
Oh, that's